Log on, tune in, find out. Another good idea from Cambridge.
Toolbox, I think we should start. So I'd like to welcome the first speaker this afternoon. It's Natig Atakishiyev from the University of National Autonoma de Mexico, and he'll be speaking on integral and finite Fourier transforms of continuous q-Hermite polynomials.
Thank you. As everybody else, I'm grateful for the possibility to be here. And I traveled a lot in Europe in general, but this is first visit to Cambridge. And I am honored to be here. I mean, read so much, heard so much, and finally I'm here in Cambridge. So, well, can we continue this, conference for a few days more? I don't know.
Well, you can stay around here.
So I have your permission at least, right? So anyway, thank you for the invitation. Now, about title. I think title already should attract some attention because this is, may I emphasize, about classical Fourier transform between functions which have extra parameter q. I hope this is a remarkable actually property, and I will try to get into that deeper. And another comment, starting comment, that why q-Hermite polynomials? So presumably we are lacking intellect or, I don't know, ambition to consider higher levels of the, in Askey-Wilson family. Everybody, almost everybody here mentioned Askey-Wilson, so or Askey-Wilson polynomials or Askey family, so probably I will not go. But I will not go to the higher level, 10 phi 9 or something like that. The reason is that not because I'm looking for simpler life at lower level of the Askey scheme, but I believe that if you know better, profoundly, special function at the lower levels of the Askey scheme, then you know actually behavior all functions on the higher levels. May I give just one example of this type? What I mean by that, not only myself, but there are some other people also thinking the same way, probably. Discovery of the orthogonality of Wilson polynomials and then Askey-Wilson polynomials. Mizan was speaking about that a lot. It was profound step in our understanding of special functions. But then 10 or 15 years later, it turned out that if you know orthogonality on the level of the q-Hermite, which are in Askey, the lowest level, then you can move step by step and come to the orthogonality and weight function for Askey-Wilson polynomials. So that's example which I keep in my mind and trying to concentrate on simpler case of the q-Hermite polynomial. So I will be speaking about, this is joint work I forgot to mention with my wife and co-author, she's also here. So this talk should be considered as a mini review about q-Hermite polynomials and their properties. Because at this stage, I think that we know about q-Hermite, continuous q-Hermite polynomials as much as we know about classical and beautiful family, which is called Hermite polynomials. Although historically it's known that there are at least 3 or 4, including Chebyshev, scientists who considered actually those polynomials before Hermite. So, but it doesn't matter. So we will stick with historical. So this is classical Fourier transform. I will be speaking about this transform. Classical formula, so I will just go on. So everybody knows that. And I will try to discuss that this family of q-Hermite polynomials possess beautiful symmetry with respect to the classical Fourier transform. So I start with definition, actually. This is the definition of q-Hermite polynomials. Three-term recurrence relation. Everything is explicitly written, everything is clear. There is initial condition, and then you can generate these polynomials. They were discovered, I think it's on the next page, by Rogers at the end of 19th century I think in 1984, something like that. And, sorry? You mean 1894? 1894. You mean that, right?
That's what you mean too.
Yeah, okay. so you felt that I am, it's on the next page actually. So last on this page, formula 2,2 is the explicit formula for these polynomials. Observe that we cannot write explicitly in the form as there is precise dependence on variable x. So we need to introduce new parameter, cosine theta, and then cosine theta is the variable. And then this is some type of the finite Fourier expansion of the Hermite polynomials, right? Finite formula. Then, right, as always Mizan was right, so dates are here by Rogers, but the point is that again, we needed to wait almost 1 century in order orthogonality relation for the q-Hermite polynomials were proven explicitly. That was done by Canadian scientist Alloway. So they are orthogonal on the finite interval -1, 1. And sometimes we exaggerate situation and we say that q-Hermite polynomials live on finite interval. The reason why we're emphasizing that because you can actually look at the q-Hermite polynomials as this version, compactified version of the Hermite polynomials, which have this weight function on the whole real line. So this is precise orthogonality relation. And then, of course, you can ask me what is the weight function in formula 2,4. It's theta function. One of the reasons probably we waited so long that it turns out that weight function in the orthogonality relation is the classical Jacobi theta function. The formulas are on the screen. Okay? Now, one more formula which I need probably later. This is again generating function for the Hermite polynomials. This part is all what I'm talking about now. It's all known, nothing new. And Tom Carminder here, he is very unbiased referee usually. And by the end of my talk, he will make comment which was new and which was old, actually. He is very strict about that. I'm afraid very much and ask him not to be very strict with me, right? So this generating function written in terms of the so-called q exponential function, and q exponential function both in the form of the infinite series and in the form of the infinite product are written on the last line on the screen. Okay? So the previous line is the linear generating function for the q-Hermite polynomials. And naturally, when q goes to 1, you should rescale a little bit variable, and then in the limit you actually reproduce or you go back to the classical Hermite. This is beauty also, another beauty of this system, that when q, which we call deformation parameter, goes to 1, you go back to the classical case. This is formula 2,7. And then all those, formulas were we suppose that q is less than 1, parameter of deformation q than less 1. So what happens if we want to look at the case when q is larger than 1? So that was observed, first Richard Oskey observed that actually that's interesting. Passage from q from less 1 to larger than 1, in some sense equivalent of the making variable pure imaginary. So you just rotate your axis, real axis, and it goes to the imaginary axis. So this is formula 2.8. This is what Richard Oskey suggested to introduce. And now at the left, again we have parameter q between 0 and 1, although this corresponds to the case when q is larger than 1. This is just for convenience, right? There is not any trick or whatever. So this is precise, formula 2.9, it's not important. What is important, and later on, actually inspired by this ASCII idea that one should connect, actually should know how to interconnect q less than 1 and q the larger one, we came to understanding that one should actually introduce this type of parameterization for the variable. Classical ordinary approach is the variable is cosine theta. But what we suggest is that when q is less than 1, you should consider variable sinus kappa s, where kappa is actually q. Formula is written over there. Should I, is there any, yes, I have. Please observe, that's very important point, and q and kappa interrelated in this way. So we actually put q here also in the argument, in the independent variable. And beauty of that is that when you make transform from q to 1 over q, you automatically go from that to that. There is now no need to make transformation in the variable. It's done automatically. So that's all about parameterization. Then in new parameterization with kappa s, this is q less than 1 case, this q larger than 1 case. Then I almost finished with this long introduction. This is difference equation, or q difference equation for the Hermite polynomials. This one. Oh, I'm sorry, this one. So this shifts by I kappa, minus I kappa, acting by this shift operator acting by that, gives you again Hermite polynomials. And then this is generating function in terms of the new in new parameterization. This is not so important, actually. And proof of this, explicit proof of these formulas, I will just skip over that. I have only half an hour. So now, briefly, I remind you case of the classical Hermite functions. When I say function, it's not only my invention. It's usually what mathematicians call this combination Hermite polynomials multiplied by Gaussian factor. So these are Hermite functions. Physicists call them harmonic oscillator wave function, definitely. But it is the same, right? So then this is second order differential equation for the Hermite polynomials. And this is very important for me, and all mathematicians know that. So then when you take actually classical Fourier transform of the Hermite functions, then you go back to the Hermite functions, multiply by some factor, constant factor. So Hermite functions are reproduced, and this pure mathematical fact fundamental part of the quantum mechanics where you should formulate your theory either in coordinate or in momentum representation. And then you ask yourself how they are interconnected. The answer is simple: Fourier transform. And this is our result, which is, I think it's important. It turns out that these Q, as I said, q-Hermite polynomials possess this beautiful property with respect to the classical Fourier transform. You take kernel of the Fourier integral transform, you take usual Gaussian factor, you take your Hermite polynomials for q less than 1, and you get the same factor, Gaussian factor, and polynomials, q-Hermite polynomials with q larger than 1. Naturally, this formula goes, when q goes to 1, goes to classical formula, which tells us that Hermite function reproduce under Fourier transform. So you may ask me how to prove that. It's easy. Proof goes something like 3 lines. You put here Fourier expansion, which I wrote before. Actually, that was reason for writing down this. You put here, and you evaluate integral explicitly by using the fact that Gaussian factor is reproduced under Fourier transform. That's it. And then you come to this formula. About limit, I said, since these are in the limit coincide with that, so this formula reproduces classical result about Hermite polynomials. So probably next step is to think about eigenfunction of the Fourier transform. Since Fourier transform actually transforms also q from less than 1 to larger than 1, it's clear that these functions are not eigenfunctions of the Fourier transform. But if you know this transform, it can be easily done. So you introduce this linear combination of polynomials with q less than 1, q larger than 1, and then you show explicitly that this combination is eigenfunction of the classical Fourier transform. I emphasize that here your function depends on the deformation parameter q, but kernel does not depend on this parameter q. And almost finishing talk, almost, I would like also briefly to discuss finite Fourier transform. Finite Fourier transform, this is definition of the finite Fourier transform, where n, capital N, is some number, then it's convenient to consider indices running from 0 to n minus 1, and that's the definition of the finite Fourier transform and eigenfunctions of the finite Fourier transform. So this is actually n by n matrix. It seems to be so simple formula that sometimes people think that, well, we should not even consider that, but Gauss considered that it's worthwhile to study them, and his famous quadratic sums came out of the study of the finite Fourier transform. Gauss was at that time 19 years old, by the way, but this is, I am myself rather old guy, so I mean, don't be offended by this remark. I mean, it's referring to my age, not to yours. Okay, so this is eigenfunction of the finite Fourier transform. And when you ask how to build them explicitly, so it was Mehta who showed actually that one can construct eigenfunction of the finite Fourier transform. And I forgot to mention, and that's important, right? Already from this formula, you see that shifts of indices j or k by capital N doesn't change here, nothing, right? Because then you are getting here exponential function 2 pi I multiplied by integer. Well, this is just 1, so nothing changes. So everything in this picture should be periodic, actually, n periodic, right? So that follows from the definition. So the reason why I am bringing that to your attention, that Meta did that actually ingeniously, because he knew that he should build this periodic function, and he knew that Hermite function doesn't have any periodicity, but that was his answer to the challenge, actually. How to do that? Take infinite sum of the Hermite functions, and then this sum, you can check that easily, will possess actually periodicity property with respect to n, because shift by capital N here equivalent to changing n, small n, by 1, and then since this sum is two-sided, then nothing changes, so you have periodicity. And these meta eigenfunctions are, this function are eigenfunction of the finite Fourier transform with the values. So, yeah, okay. There will be some prize if I finish earlier, right? Yeah, okay. So what we did actually, we showed that by using our result for the classical Fourier transform, one actually can build as well eigenfunction of the finite Fourier transform. And I, again, in this paper, we thank actually Tom Carwinder for bringing to our attention of one paper of Dalius, I think the author, Dahlquist, okay. And who actually, after Meta did this work, he proved in more general form that actually classical integral transform actually gives you possibility immediately construct eigenvectors of the finite Fourier transform. So in that sense, our result follows from this general statement, but we think that still explicit form of these eigenvectors of the finite Fourier transform in terms of the q-Hermite polynomials deserve some attention. So I hope that I convinced you that continuous q-Hermite polynomials are beautiful. One should study them and respect them. Thank you.
Do we have any questions?
Suppose we are all spellbound.
Oh, no. Thank you. Nevertheless, thank you.
No questions. Could we thank the speaker again, please?